this lecture, we're going to look at a few types of vector norms. First one is the most commonly used norm, which is known as the Euclidean norm, or the L2 norm. The L2 norm of a vector x given by, so we have a vector which is having n components. You take x1 squared plus x2 squared plus etc. plus xn squared. Square of all the individual components and take the square root of this. This is L2 norm. So this is also a derived norm. In fact, it is derived from the inner product, which is the most commonly used inner product, which is the dot product. So L2 norm is actually inner product, which is in fact x transpose x dot product. Okay, this is the most commonly used norm. So why is this called the Euclidean norm? Because it gives the Euclidean insistence between two vectors. So for example, if we take this norm, this gives the Euclidean distance between x and y. So it's normally commonly called as the Euclidean norm. Second norm is the L1 norm. It's also known as the sum norm. Or other names are taxi cab norm or Manhattan norm. X1 norm is given by, squares here. We're taking the modulus of each component of the vector and adding them together. Is also a vector norm. We can prove that this norm for satisfies all the properties of a vector norm. That is non-negativity, positivity, homogeneity, and triangular equality. Another norm is the max norm, which is L infinity norm. Max norm. L infinity norm. The max of x1, x2, etc., x3. Max of modulus. So that's also something which is important. Max of modulus of all the components of the vector. And finally, we can also define an LP norm. One thing to notice here is, okay, let me first define LP norm. This is sigma I equal to 1 to n modulus of xi raised to p all raised to 1 by p. where P is greater than or equal to 1. So one thing notice here is when P is equal to 1, still be an L1 norm. P is equal to 2, this is an L2 norm. And P is equal to infinity, this will become an L infinity norm. For values less than 1, it is a norm. So it will not satisfy all the properties. Also not. For such cases where it's not a norm, just have to take one contrary case and show that it's not a norm. Okay. So one more thing we have to notice here is, suppose we define a norm like this, norm of x star is equal to minimum to etc. This is not a norm. So one of the first things which comes to your mind here is it will not satisfy non-negativity for sure, because when we are defining minimum, if any of the components is a 0, but that vector need not be 0, but the output of the vector will be 0. So it does not satisfy non-negativity. Also, you can show that it does not satisfy triangle inequality. Okay. Fine. Using a counter example, we can show that it does not satisfy triangle inequality. So one more note is triangle inequality for P norm is x plus y, P norm is less than or equal to P norm of x is P norm of y, where P is greater than or equal to 1. This is known as the Minkowski inequality. Okay. Fine. Let's also look at the shapes of these norms. So let's say we have a vector v such that norm of v2 is equal to 1. Let's say we look at all the vectors in a vector space which satisfies this condition. Then what will be the shape of, what will be the locus of the points which satisfies this condition? This will be a circle norm of v is equal to 1. This will be the locus of all the points which satisfy this condition. What about infinity norm? So let's say, let's look at the case where b infinity is equal to 1. What does that mean? The max value of the modulus is 1. So whatever value uh, the other components have, the max value is 1, right? So this is a 2D case which you're looking into. So all the vectors which line the x-axis, of course, has a value 1, right? Now, all the vectors with value when y component as 1 will have this. But in the middle, it doesn't matter. All these vectors this will should form a square, right? Yeah, this is the locus of all the points. And if you look at L1 norm, where the modulus is 1, and the magnitude, sum of the magnitudes is 1, so you'll find that it will form something like this, something like a diamond shape. Yeah. So these are the locus of the points. 2D. Let's conclude this discussion here.